In the rest of this lecture, we want to use the material we've developed so far to classify groups of given order using semidirect products. So the goal is going to be, we'll take an order n, and we want to come up with a list of groups so that every group of order n is isomorphic to something in our list. So we've already done this in some examples. For example, we classified groups of order 6, groups of order p when p is a prime, groups of order p squared when p is a prime. And we now have the tools to classify more groups of given order like this. All right, so the idea is the first big step is that we're going to show that every group of order n has proper non-trivial subgroups h and k, so that hk is the whole group G, h intersect k is the trivial subgroup, and h is a normal subgroup of G. So what is that going to tell us? That means that G is isomorphic to the semidirect product of h and k determined by phi, where phi is the homomorphism of k acting on h by conjugation. So what this will say is that every group of order n is a semidirect product. So this is not always possible. In the last video, we saw, for example, that when n equals 8, Q8 is not a semidirect product of two of its proper subgroups. We also saw that when n is p to the k, more generally, the cyclic group of order p to the k is not a semidirect product of two of its proper subgroups. This doesn't mean there's nothing we can do in the case where n is a power of a prime, but we might have to have certain special cases, like either every group of order n is abelian, or it's non-abelian and is isomorphic to some group in this finite list. All right, so if we can show a statement like this, that every group of order n is isomorphic to a semidirect product of two smaller groups, the next step in classifying is to determine all possible isomorphism types of h and k if you have two subgroups h and k of G that satisfy these three properties. So these are going to be groups whose order is smaller than G, divides G. So if we've classified smaller groups, we want to use classifications for smaller groups to get the classification of groups of order n. So now, if we have a pair, let's say H is isomorphic to some group, K is isomorphic to some group, we want to say, what are all the different ways that we could form a semidirect product of those two groups? Well, a semidirect product is determined not just by the groups H and K, but also by a homomorphism from K to the automorphism group of H. So if we know what H and K are, we can determine what all these possible homomorphisms are. And now, for each one of these triples, H, K, and phi, we can form the semidirect product of H and K with respect to this homomorphism phi. And if n is not like too simple, we're just going to get like a huge list of groups. And some of these semidirect products will be isomorphic to each other. So we then need to do something to determine which of these groups that we got from this process are isomorphic to each other. OK, so the next thing that we want to do in this video is show how to carry out this process when n is equal to p times q, where p and q are two primes and p is less than q. In the rest of this video, we'll talk about classifying groups of order p times q, where p less than q are primes. And first, I want to review a little bit about what we know from using the Silo theorem. So let's say G is a group of order PQ. Let's say P is a Silo P subgroup and Q is a Silo Q subgroup. So we've already seen that Q has to be a normal subgroup in G. And there are two different ways that we could see this. One, what is the index of Q in G? It's P. And that is the smallest prime dividing the order of G. So we already saw that if you have a subgroup whose index is the smallest prime dividing the order of the group, it's automatically normal. Another way is by using CeLO 3. We know that NQ, the number of CeLO Q subgroups, is 1 mod Q, and NQ divides P. But P is a prime, so the only things that NQ could be are 1 or P. But it can't be P because P is not 1 mod Q, because P is less than Q, and it's not 1. So that means that the number of CeLO Q subgroups is 1, so that unique CeLO Q subgroup is normal. So what does CeLO 3 tell us about the number of CeLO P subgroups? Well, it's 1 mod P, and it divides Q. So it's 1 or it's Q. If it's 1, then we have a unique CeLO P subgroup, a unique CeLO Q subgroup. Those are all the non-trivial CeLO subgroups. And we see that G is isomorphic to a direct product of its unique CeLO P subgroup and its unique CeLO Q subgroup. So if NP is also 1, then G is going to be cyclic of order PQ. If NP is Q, that means that Q has to be 1 mod P. So what have we seen? If Q is not 1 mod P, then G is cyclic of order PQ. So now let's look at the case where Q is 1 mod P. What can we say about Q and P? Well, we know Q is a normal subgroup in G. The intersection of these two subgroups is trivial, just by Lagrange's theorem. So what does that mean about the subgroup QP? Well, the order is the product of the order of Q and the order of P, but that is the order of G. So QP, which is a subgroup because Q is normal, is all of G. So now we have two subgroups, Q and P. The intersection is trivial. The product is the whole group, and Q is normal in G. So by the recognition theorem for semidirect products, G is isomorphic to the semidirect product of Q and P with respect to phi, where phi is the action of K on H by conjugation. But what are K and H here? It's the action of P, on Q by conjugation. So one thing we could ask is, what is this action? Is it non-trivial? So I'll pause and erase, and then I'll talk about what this semidirect product could possibly be. We've now seen that this group of order PQ is a semidirect product of a CeLO Q subgroup and a CeLO P subgroup. But let's talk more about what that semidirect product is. So to recap, P less than Q are primes. We're in the case where Q is 1 mod P. G is a group of order PQ. P is a CeLO P subgroup. Q is a CeLO Q subgroup. We have seen that QP is the whole group. These two subgroups intersect in the trivial subgroup, and Q is normal in G. So G is isomorphic to Q semidirect product P with respect to phi, where phi is some homomorphism from P to aught Q. We know a lot about P and aught Q. P is isomorphic to Z mod PZ. So we can choose a generator and say that it's generated by Y. We know that the automorphism group of Q is isomorphic to Z mod QZ. So the automorphism group of Q is isomorphic to the automorphism group of Z mod QZ, which is Z mod QZ star, an abelian group of order Q minus 1. And what do we know about Q minus 1? Since Q is 1 mod P, P divides Q minus 1. So by Cauchy's theorem, the automorphism group of Q has a subgroup of order P. So that subgroup has to be cyclic. Let's say that it's generated by gamma. Gamma is some automorphism of order P. So we want to understand what all the different possible homomorphisms from P to aught Q could be. Well, P is a cyclic group. So a homomorphism from P to aught Q is determined by where this homomorphism sends a generator of P. Let's say Y, this particular generator. So the order of Y is P. So what kind of element could y gets sent to under this homomorphism? Well, it has to have order dividing p. But the only things dividing p are 1 and p. So either phi y is the identity of aught q, and you have the trivial homomorphism, or the order of phi y is p. So where can you send phi y? It can go to any automorphism of q of order exactly p, and that will give you a non-trivial homomorphism phi. So how many non-trivial homomorphisms phi are there? Well, as many as there are elements of aught q of order p. So we can just pick one and say, if we say phi y is gamma, this determines one non-trivial homomorphism from p to aught q. And for this particular phi, q semidirect product p with respect to phi is a non-abelian group of order pq. So this is a really good start. But what we want to do is say that every group of order pq is isomorphic to either this group or this group or this group or this group. So we don't just want to construct one non-abelian group of order pq. We want to construct a full list of groups of order pq up to isomorphism. So I'll pause and erase, and then we'll complete this classification. We'll have to bring in a couple of outside facts in order to finish this proof. We saw how to construct one non-trivial homomorphism from p to aught q. So the next question is, what if we had picked a different homomorphism? That first homomorphism gave us a non-abelian group of order pq, the semidirect product of p and q, or of q and p with respect to phi. But what if we change phi to a different homomorphism? Like, for example, we could define phi by saying that phi y is, instead of being gamma, it could be gamma to the I for any I from I goes from 1 up to p minus 1. These p minus 1 homomorphisms are all different. We're always sending a generator of p to some element of order p in aught q. So every time we're getting a non-trivial homomorphism, and these homomorphisms are all different because they send y to different places. So that gives p minus 1 different non-trivial homomorphisms. Are there any more? So a fact that we will not prove now, but we'll prove later in the 206 sequence, is that z mod qz star is cyclic. So what does that tell us? It's a cyclic group of order q minus 1. And that means that it has a unique subgroup of order d for each divisor of q minus 1. So in particular, it has a unique subgroup of order p. So that means that there's exactly p minus 1 elements of order p in z mod qz star and in aught q. And what are those elements of order p? We already named them. They're gamma, gamma squared, gamma cubed, up to gamma to the p minus 1. So what does that mean? That means that the only non-trivial homomorphisms from p to aught q are determined by saying which one of these p minus 1 elements of order p are we sending y to. So what does that mean? Every group of order pq is either cyclic or it's isomorphic to q semidirect product p for one of these p minus 1 non-trivial homomorphisms phi. So now let's zoom in a little bit on these p minus 1 different semidirect products. There is an exercise that you proved on the homework, exercise 6 of section 5.5, which says when k is cyclic and h is any group, if phi1 and phi2 are homomorphisms from k to aught h such that the image of the first homomorphism and the image of the second homomorphism are conjugate subgroups of aught h, then the corresponding semidirect products are isomorphic to each other. So I'll pause and erase and write down the details of how we use this exercise to complete the classification, but maybe you can see it already. In this case, K is equal to P is this cyclic group. And what do we know about the image of phi1 and the image of phi2? Well, they're subgroups of the automorphism group of H, which in this case is the automorphism group of Q, which is isomorphic to Z mod QZ star. If we pick phi1 and phi2 to be two of these homomorphisms where we send Y to an element of order P, then these images are going to be subgroups of the automorphism group of Q of order P. And how do we know that they're conjugate to each other? Because aught Q is cyclic using this fact, which means it has a unique subgroup of order P. So not only are these subgroups conjugate, they are equal to each other. So that'll say that any one of these p-1 different semidirect products that come from choosing these p-1 different non-trivial homomorphisms, they all give isomorphic groups of order PQ. Let's use this exercise to finish the classification of groups of order PQ. We know that there are exactly p-1 non-trivial homomorphisms, phi1, phi2 up to phi p-1 from P to aught Q. And for each one, the image of that homomorphism is a subgroup of aught Q of order P. But we also know that aught Q is cyclic of order Q-1, so it has a unique subgroup of order P. So not only is the image of phi I and the image of phi j, not only are these conjugate subgroups, but they are actually the same subgroup. So by this exercise, all of these Q semidirect product P with respect to phi I, all of these semidirect products are isomorphic to each other. So now let me just state this result about classifications of groups of order PQ as one single proposition. Let's say that P less than Q are primes, and G is a group of order PQ. If Q is not 1 mod P, then G is cyclic. If Q is 1 mod P, then either G is cyclic, or if it's not, it's isomorphic to Z mod QZ semidirect product Z mod PZ, where phi is a non-trivial homomorphism from Z mod PZ to aught Z mod QZ. And the thing at the end of this statement is saying that it doesn't matter which non-trivial homomorphism you pick, that you'll always get the same non-abelian group of order PQ.